we're going to be looking at kinematics problems where we have two moving objects and determining when they are in the same location.
What did I miss yesterday?
We did, it's on the video there, Chandler, but we did some more textbook examples, slightly more challenging ones. This is level 3 of the example questions. Okay? I'm going to do 2 problems today, and then I'm going to give you some time to work. On Monday, we'll do a little bit of a quiz, temperature check to see where we're at. So hopefully you've done some practice. Maybe you can do a few problems over the weekend or something, because we need to be moving on soon and get into that first test. So we will determine that very soon.
Where's this example?
This is example 12 from the textbook. You should have it in that example package that you got yesterday. Fred and Barney are at opposite ends of a 1 kilometer long drag strip in their matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second squared. Barney travels toward Fred at a constant speed of 10 meters per second. How much time elapses until they collide? I'm going to get my notes because I always mess this up. Okay, so let's just assign one of these guys to be Fred and one to be Barney. Let's call Fred over here, and we'll choose that to be Barney. And when they collide, and this distance here is how far? 1 kilometer. Should we convert that to meters? We should. Let's call that 1,000 meters. And at some point, they collide here in the middle, and they crash, right? Is it right in the middle at 500? How do you know? Yeah, one's accelerating at 2 meters per second. He's going, like, increasing in speed. And this guy's going at a constant speed, right? So which side would you say it's on? When it's on the left-hand side, closer to Fred or closer to Barney? Closer to Fred because he goes considerably faster, right? Now that's assuming, what if it happened in 2 seconds? This guy'd only be going 4, and this guy'd be going 10, so he would have traveled farther, right? But you're using your intuition, and you're saying, well, it's 1,000 meters, it's likely going to be a considerable amount of time. This guy's going to be going faster than this one, so it's likely going to happen like over there, right? Is it not? Okay. So what is true about the time when they collide? Like Fred's time and Barney's time are 2 different variables, but when they collide, they should be the same, right? So do you guys have a half a page or a full page? Full page, good. At collision time Fred is equal to time Barney, right? The times are equal. What else is equal? It's blatantly obvious. So obvious that you might not see it. No, not their velocity. Remember, this guy's going faster, faster, fast, right? What's that? Well, I guess after collision, 0, I suppose, right? Their position. They collide when their positions are the same, right? But Barney is not at the start, right? Fred is here. Should we mark one like it's 0? Position 0, and the other one would be at position 1,000. Barney starts off at position 1,000. When their positions are the same, they collide, and at that point, their times are the same, and we can figure that out, right? Okay, so that's sort of the setup for the whole thing. So Fred, let's just say position Fred. Position Fred, position F is equal to his displacement. Right? Whatever change in position, that's his position. And because he's accelerating, his displacement is d equals VIT plus 1/2 AT squared. Fred's position is equal to his displacement, which is equal to VIT plus 1/2 AT squared. Position Barney is not equal to his displacement because his position is measured relative to the 0. So what is his position? Well, initially, his position is, he's at position 1,000, absolutely, good. But he is displaced, so his position is actually 1,000. Now, would you say minus his displacement, or would you say plus his displacement? And actually, the answer is either one is fine. You would say minus? And we want to say plus, because I'm okay with that. Minus his displacement. So that's going to be, as a formula, is going to be 1,000 minus, what's his displacement? Well, he's traveling at a constant 10. So his displacement is his velocity multiplied by his time, which is 1,000 minus 10t. Right? If he goes for 1 second, he goes 10 meters left, and his position is 1,000 minus 10, or 990 meters. Position 990. Does that make sense, Brandon? Every second he goes 10, 20, 30, 40, 50, 60, right? And his position is 1,000, 990, 980, 970, 960, and so on, right? And when these two are the same, well, that's when they collide. So what do? Make them the same. Make them equal to each other. Make this equal to this one. So in other words, VIT plus 1/2 AT squared is equal to 1,000 minus 10t. Set them equal to each other. Set their positions equal to each other. Can you solve that? Well, fortunately, the initial velocity is 0, right? So 0t, so that sort of drops off. So it's 0 plus 1/2. What's the acceleration of Fred? 2. So conveniently, 0 plus 1/2, 2 is 1. Fred's position is, in fact, t squared. All that work, and I get down to t squared. If Fred accelerates for 1 second, 1 squared is 1, he's gone 1 meter. 2 meters, he's gone 4. 3 seconds, he's gone 9. 4 seconds, 16 meters, and so on. Over here, I've got 1,000 minus 10t, and in fact, I can't plug anything else in there, so I got t squared is equal to 1,000 minus 10t. Can I solve that? I only have t's in there. I have t and a t squared, though. How do I solve it, Jared? Remember from yesterday? No? Quadratic formula. Right you are, Ryan. And how do we do that? We put everything to one side and we go t squared. The minus 10t goes to the other side and becomes plus 10t. Minus 1,000 equals 0. How's your factoring?
That's the exact same thing, a different way.
I'd like to hear that. And when I'm done, what? Could you factor that? Factors of 1,000 that add or subtract 10. It seems like you should be able to, right? I'm guessing you won't. You could try. I know the answer because I have it here, but I don't think you'd get it. Well, they're kind of weird numbers. They are integers. They may be rounded. I'm not sure. But nothing pops in. Like, I mean, it could be like 502, 250 and 4. What? 5 and 200. 10 and 100. Like we're not getting anywhere here, right? Should we just go quadratic formula? Okay. Okay, so quadratic formula is x equals minus b plus or minus square root b squared minus 4ac all over 2a. What are my a, b, and c values? Minus b is going to be minus 10 plus or minus square root b squared is going to be 10 squared. 4a is 1, nothing in front of that one. C is negative 1,000. All over 2a, which is over 2. Minus 10 plus or minus, we might be able to do this. 10 squared is 100. Minus 4 times 1 is just minus 4. Minus 4 times 1,000 is plus 4,000, right? 100 plus 4, so it's square root 4,100 all over 2. And when you do that, you're going to get, and I don't know, do I need to go through that next step, or can I just jump right to the answers? Jump? Like you're going to go square root 4,100, you're going to add it to minus 10, and then divide by 2. And then you're going to take 4,100, you're going to subtract that from minus 10, square root, divide by 2. And you end up with either 27, or the other one is minus 37. 27 or minus 37 what? Well, you're solving for t, so these are in fact both seconds. Would you have been able to factor 27 and 37? Did you know 27 times 37 is 1,000? The only, yeah, it's not actually as it is. Yeah, it's kind of rounded, so it's pretty much impossible to factor. Seems like it should be, but it's not. Okay, so minus 37, is that a possible time? 37 seconds ago, you collided. No. So the answer is 27 seconds. And if you wanted to know where, because generally they like to ask you those kind of questions too, right? How do I figure out the where? You could plug that 27 seconds into either this one or this one, and you'll get the same answer, right? I'm going to plug it into the easy one, which was 1,000 minus 10t. 1,000 minus 10 times 27, which is 1,000 minus 270, which is 730 meter mark is where they collide. Yeah, tell me.
So, Fred is accelerating one way, Barney is accelerating the other way.
Yeah? No, Barney's going constant speed. Yeah.
So, if you take Barney, flip him around, and add his velocity onto Fred's acceleration, then you essentially are just replacing VI as 10.
Okay.
So it's like you have Barney turned into a train and Fred's accelerating on the train, and it's the time it takes for Fred to travel 1,000 meters along the train.
Oh.
You get the exact same answer. Like,
Yeah, I get it.
yeah.
No, seriously, my head just went boom.
Yeah.
Yeah. Yeah, I get you. That's cool. I've never seen that.
I put.
Okay, well, let's try it. We'll try the next one your way. No, you'll try the next one your way.
But I already tried this one my way.
Example number 13 is almost the same with a twist. It's an M. Night Shyamalan physics problem. Here, Jack is running to catch the bus. He sees it start to move when he's 20 meters away, so the bus has a head start. The bus is accelerating, and Jack is already running at a constant 6 meters per second. He can't run any faster because he's wearing dress shoes and a suit. Will he catch the bus?
Probably.
Is this the same type of problem? It's two objects. You're looking for the time. Instead of going like this, right? Like Fred and Barney, I had like 1,000 minus 10t. Here it's going to be the bus. It's going to be positive. Want to try that one on your own? Try that as a setup. I'll give you a few minutes while I do attendance, and then I'll do it. Okay? Give it a whirl and see if you can figure it out. Give it a good honest go. The answer is always the positions have to be at the same position, right? So we're going to mark this at 0, and we're going to mark this position at plus 20. Could I have marked this one at 0 and this one at minus 20? Absolutely would have worked. Just doesn't feel right. Okay. And position of Jack is equal to his displacement, right? And Jack is already running at a constant 6, so it's v bar t or 6t. His position is equal to 6t. At 1 second, he's at the 6 meter mark. At 2 seconds, he's at the 12. And that's how Jake figured it out, right? He figured out where he was at each second and where the bus was. Position of the bus is equal to the displacement, but plus 20, because he had a 20. The bus has a 20 meter head start. And the bus is accelerated. So that's going to equal VIT plus 1/2 AT squared plus 20. Initial velocity of the bus, 0 times t, plus 1/2 the acceleration of the bus is 1 t squared plus 20. And when you cancel that all out and simplify, 1/2 of 1 is 0.5 t squared plus 20. 0.5 t squared plus 20. And again, Jack catches the bus when those positions are equal. So how do we find out the time when they're equal? Make them equal. So I'm going to write 6t is equal to 0.5 t squared plus 20. That make sense? Is that the same setup as the previous example? It's almost identical, right? Almost identical. Same sort of idea. Now we solve it. We all like to have our t squareds positive in our quadratic formula ones. So I'm going to have 0 equals 0.5 t squared. The 6t becomes minus 6t plus 20. You want to factor that? Probably not. X equals minus b plus or minus square root b squared minus 4ac all over 2a. Careful here. The b is minus already, so it's minus b minus minus 6 or 6 plus or minus square root. B squared is going to be minus 6 squared. Do I need to write the minus 6? I guess for sake of completeness you should, but it's not going to matter. Minus 4. The A is 0.5. The C is plus 20. All over 2A. 2 times 0.5. Six plus or minus all over, well, let's do 2 times 0.5 is just 1, right? I don't even need that really. Square root, this looks complicated, so I'm going to do it in steps. Minus 6 squared is going to be 36. Minus 4 times 0.5 is minus 2 times 20 is? And what happens? You got 6 plus or minus the square root of minus 4. And what does that mean? No solution. There is no time when their positions are the same, as you guys determined by brute force. But I saw you had to think about it when I said, well, there might be a 3.5 seconds, right? And that's the problem with your way is that you, right? You don't know about, and you can never go small enough increments to really determine it, right?
There are an infinite amount of integers between 0 and 1.
There certainly are. Even more? There wouldn't be double? That's an argument for another day. It's an argument for another day. No, another day. What is this under the square root sign called when you quadratic stuff? Does anyone know? Starts with a D. I don't even know if they teach it anymore. It's kind of a derogatory term. What's this thing under the square root called? Do you know what quadratic form is? Anyone know? It's called the discriminant. Ever heard that? Yeah? When the discriminant is negative, then that means there's no solution. And the reason that I show you that one is because I wanted you to see a question where there was no solution. Okay? Oh yeah, for sure. So that's why you got to be real careful with your signs here, right? Yeah. Okay, so yesterday I gave you these. I'll give it to you again. Page 64, numbers 1 to 3. And page 73, numbers 33 to 66. And you can leave out 50, 54, 55, and 60. I'm going to give you the rest of the time to work on some problems. On Monday, give me a second, Mike. On Monday, I'll give you a little quiz that I will mark and see where you're at and give you an idea of where you're at. I would suggest you do some work between now and then. And based on that, we'll determine how much farther we spend on stuff like this. It is not a clicker quiz, it's a show your work kind of quiz. Yeah. Okay, so I'm done for the day.